So here's what happens now. So we're going to have two more talks, one from Facebook and one from Xilinx. And so Andrew Tulloch from Facebook is going to tell us about TVM's use within Facebook. And then Graham is going to tell us about inference at Xilinx. And then after that, we're going to have a very short break because we're going to move on to the lightning talks that Professor Zach Tetlock is going to run. So, and then we're going to have the community formation discussion. Without further ado, Andrew, thanks for coming. Please.
Hi, everyone. I know there have been a lot of talks today, and I'll try and keep this one as brief and entertaining as possible, but I can't promise everything. So yeah, it's great to be here. I think this is probably the start of hopefully a long collaboration between Facebook and the TVM community. There's quite a few folks from Facebook here in the audience, at least 5 or 6. So we've been working internally on TVM since about June this year, since basically we came up and had a chat with TQ and sort of he convinced us that this was pretty exciting, and yeah, we completely agree. So we've been working on applying TVM to a lot of our super high throughput inference problems that we have on our CPUs and GPUs on both our server environments, which are mostly Intel CPUs, and our mobile environments. So this is more of an experience report. There isn't sort of a heap of super technical information here unlike the previous ones because there's so much exciting stuff in the lightning talks coming up. So generally speaking, at Facebook, we've got a sort of hugely growing ML inference workload, which mostly splits between our sort of ranking and recommendation systems, so the stuff that powers, say, the ads and feed models, and then our computer vision systems, which power sort of all the visual understanding that's used in sort of Facebook, Instagram, and Messenger to some extent. And so this is a huge range of tasks. So for various reasons, these still currently leverage mostly Intel CPUs, so that's like a main substrate that we're really interested in optimizing in the server side. And so here's one of the sort of slides from the archive paper we just put up showing the kind of growth which I'm sure is mirrored in a lot of places around the industry. For mobile, we're also sort of doing a pretty substantial amount of work looking to apply TVM to a huge number of problems. So the main tasks we have here are these real-time computer vision workloads, which are super latency sensitive and have to run on a huge variety of platforms. So this is stuff like our Instagram focus mode, which you might have seen, which is doing a real-time semantic segmentation, or some of our hand and body and face tracking work that we sort of expose in our various AR or augmented reality surfaces. Specifically on mobile, another sort of really interesting area for where we're excited with TVM is in solving a lot of sort of these new constraints that you get from the mobile environment, stuff like code size constraints specifically, where even sort of a tiny interpreter the size of, say, C2 or TF Lite, which is on the order of, say, hundreds of kilobytes of code, is even too much. So to give a sense for what the sort of the diversity of compute platforms for sort of apps like, say, Facebook, Instagram, Messenger, WhatsApp, you can see the incredibly long tail here in both sort of the SoCs and the mobile chipsets. So here's a couple of quick examples of sort of the stuff we can do. So here we're running a real-time mask RCNN model doing body key point detection, and similarly some object detection stuff. So this is just pretty lightweight, kind of fun. So generally speaking, the main reasons we're really excited about TVM and why we sort of have been working on it for the past couple of months have been that as we scale up our hardware, sort of as we introduce NPUs, TPUs, GPUs, DSPs, and so on, it's hard to write code manually, it's hard to write fast code manually. Similarly, the numeric side, so whether that's, you know, all the different sort of floating point formats, all our integer formats, and some of the interesting ones in between, stuff like the posit math and the sort of logarithmic domain math, where you might have seen some recent Facebook publications. Similarly, the hardware is changing a lot. As the sort of ratio of flops to memory bandwidth keeps on increasing for basically every single computational platform. The inefficiencies in our interpreters and sort of our existing kind of simple compilers are being revealed. And so it's just unsustainable to keep on going the way we are. So we started out with the goal of sort of proving that we could sort of use TVM and make it the fastest runtime available for basically every problem. At least that was the ambitious goal that we wanted to solve for all our Facebook workloads. And so this is kind of the summary of the last couple of months' work by a couple of the people in the audience. So yeah, on the server computer vision, again, this is all open source. We've worked with the community on this. So it's a very standard problem, making a model like ResNet 50 the fastest it can be on, say, even on a single-threaded batch size 1 workload. So we started out with TVM as it was, made a few modifications, open sourced those modifications, and we ended up getting pretty substantial speed-ups over our, the incredibly strong MKL DNN baseline, which we were targeting, which ended up being about 30% at batch size 1. The other key thing that a lot of presenters have talked about, and I just want to reiterate because it's incredibly important, it's not enough just to make models like ResNet 50 fast, as sort of these more heavyweight libraries like MKLDNN mostly do. Like the speed-ups that we get on our sort of non-standard models, like here one of our segmentation models, are really huge, and that's really exciting for us. So we're similarly targeting mobile computer vision environments. This is another area where we've got a really strong, or at least what we, as far as we publicly know, is an incredibly strong baseline. And we want to prove that we can beat that with TVM as well. So one big problem, generally speaking, with a lot of these code generation frameworks on ARM, especially ARM v7, is that the register allocator is pretty poor, and it's very hard to generate the exact code sequences that we want, which is where the great features like tensorization is a great safety hatch, where we can drop in our existing highly tuned, architecture-specific microkernels and get exactly the same performance as where we were before. And then if we can improve the cases where our baseline is bad, we've got a decent win. So that's essentially our strategy here. By leveraging our existing baseline for places where it was performing, incredibly well, and leveraging TVM for maybe some of the longer tail stuff, or some of, the cases it just eats up, like pointwise fusion, we get substantial improvements. So here's a case where for one of our segmentation models, we end up getting, on the order of sort of 70% improvements over, our initial TVM baseline, and about 20-30% over our production baseline, which is really exciting. The last main area that I wanted to mention, which is sort of some pretty recent work, you can see in some of our repos. Again, all of the stuff we're working on is in open source, and we're really excited about participating in this community, is in our sort of server ranking workloads. So here, the architectures aren't as public for various reasons, but you can look at cases like, say, the wide and deep networks paper, deep factorization machines, and so on, to get a sense for how these workloads compare. These are some of the most heavily used models at Facebook, where we're sort of executing these models to predict ad clicks or, user feed event interactions. Computationally, they're very interesting from a sort of performance perspective, because they're a mix of sort of a wide variety of patterns, whether we have these large, very non-uniform memory access patterns of these like sparse subgraphs where we're doing embedding lookups and even sort of tiny MLPs on top of those lookups. And then we have more standard, dense sort of sequences of fully connected ops, or sort of more complex subgraphs of these kind of dense computation patterns. So we have a variety of new NNV ops that we've implemented and tuned. Again, this is all open sourced. So here's just a kind of high-level view of some of like the architectural features of these kinds of models. the key point is that we can get really substantial improvements across a wide variety of batch sizes and a wide variety of platforms with TVM. And so we're really excited about these results. These sort of 3 results have been really encouraging in terms of proving out that we can really adopt TVM for a lot of important problems at Facebook. So there have been so many interesting pieces of work that we've seen presented here and that we will see presented. So this is just more of a couple of projects that we want to, say, work on or work with the community to implement to make TVM even better for a lot of the cases that we care about. So one major one is the sort of quantization work, which we've heard a lot about. One key point is that in a lot of cases, we've found it quite challenging to generate the right instruction sequences especially on ARM Neon via sort of standard TVM primitives. So I think in this case, a lot of the tensorization stuff we want to reuse, or at least we could reuse for a lot of these from our existing libraries. Similarly, we care a lot about, there are a lot of cases where we care about this constrained dynamism of shapes, which, projects like Relay, especially the new runtime, are going to be really exciting in addressing. So these are cases where we say change our batch size in ranking, our sentence length in NLP, the spatial dimensions of images which we use in, say, FCN models or some of our large-scale object detector models. And another thing that we're also really excited about is some of the work in the auto-scheduling case to sort of have a fallback in the cases where the dynamic structure of our inputs isn't well handled by our sort of AOT'd kernels. And then on the mobile side, there's a bunch of kind of interesting work we're excited about sort of contributing to, an Android, an open source Android open GPU backend that can sort of be widely deployed and provides, reliable performance improvements would be an incredible asset to the community. And we think TVM is a great opportunity to do that properly. Similarly, work around the DSP, the interpreter bundling work from projects like Relay is very important. And another area that I really want to shout out is Meghan and others' work on ultra-low precision. One thing we notice really is that in a lot of cases, it's hard to incentivize people to sort of work on these kind of areas when the runtime support isn't really there. But projects like TVM, and especially the TVM mixed precision and ultra-low precision work, is really exciting in overcoming that hurdle. That's the end of my talk. Thanks so much, and I'm really excited about the rest of the talks here. Thanks.
Yeah, Rick, here.
Hi, thanks very much for the talk. I'm curious how this work with TVM might overlap with other research that we've seen, like tensor comprehensions and the work in GLOW.
Yeah, there are a couple of interesting directions there. I mean, with respect to Facebook specifically, a lot of work in tensor comprehensions has been put on hold since most of the authors, or like the main authors, left the company basically, and are working on different projects now. GLOW is targeted toward hardware accelerators, and we're not addressing hardware accelerators with TVM right now. That's not a focus of our work. But generally speaking, the community's work in hardware accelerators is amazing. With TVM, we're really excited about that as well. But yeah, they're mostly orthogonal projects currently.
More questions? Okay, well, thank you again, Andrew. Thanks for being so open, too. Thank you. All right. So we have the last of our longer talks before lightning talks by Graham Schelle. Am I saying Schelle? I should also say thank you very much, Xilinx, for supporting Sample. Very appreciated. Thank you. And also use that one. Sorry, yeah. And there's a clicker there. So if you want to move around, this one is too.
Okay, Hey everyone, so thank you for having Xilinx here. We're big fans of TVM. We're just learning more from Louise and mostly we've been talking with Thierry, but I'm also an alumni at University of Washington, so it's great to come back. So the talk I'll talk about the inference architectures that are at Xilinx today. As you can imagine, I was surprised to hear FPGA mentioned so many times in the earlier talks, and I'll try and tailor some of the talking points to some of the good work we've seen so far and my guess as to the lightning talks that are coming. And so we have nice headlines that come out with some of our cloud partners where databases are doing 1 million transactions per second, Alibaba Cloud, in their Cloud 11 days, like their Black Friday, right? We see things nice like that. If anyone here watches esports, we're seeing FPGAs being deployed by Twitch. If you're not familiar with esports, it's just watching live gamers. And in 2007, this is a rough talk. No, everyone's against me. But esports are really fun. So like the Super Bowl in 2017 had about 100 million people. They predict by 2020 there'll be esports final events. They'll have 70 million viewers simultaneously. So what's fun about that is video as an application has clearly latency requirements, and so FPGAs play well in that space. And good stories also in the medical field where gene sequencing companies are breaking records, world records, for how fast you can go from pinprick of your blood to a sequenced DNA. And so it goes from come back in a week to if you can wait 20 minutes. So it's a wonderful, I bring these examples just to show it's a wonderful time for computer architecture research, and FPGAs can play a big part of that. So I'll talk a little bit about, bring everyone up to speed with the Xilinx as it is today. We've had a lot of announcements of our own, and I want to just, if you're not familiar with the FPGAs, take 2 slides to talk about that, but then move into where we're at with inference architectures and where we see FPGAs playing in the space, and wonderfully, hopefully be a TVM target across our architectures as well as Vita. And my role kind of at Xilinx, being in the labs, is a proponent of open source, and so I maintain one of Xilinx's most popular open source projects called Pink, which has been mentioned a couple times, and if you've seen Pink boards on the slides, a marketing win for Xilinx. But so traditionally, my 2 slides on FPGA, very short history. Traditionally, they've been massively data parallel for applications. So great transceivers out of the gate, massively parallel at the bit level typically. But then, over time, they've kind of evolved, like a lot of architectures, right? And, in 2011, I was actually working in Intel research, and we didn't really like ARM that much because we were trying to get into mobile, and ARM was kind of seen as the embedded processor of the time, and Xilinx was integrating ARM processors with Fabric on a single die. And then in 2015, that work continued with ZU Plus, Zinc UltraScale Plus. We were adding more of the A53s that were mentioned as being in mobile, and that was to target embedded, right? There was a push to be an embedded application player, and everyone was attaching ARMs to FPGAs or processors to FPGAs. Xilinx decided to just integrate it together. And more recently, and this gets to talking to Michael after the Hammerblade talk and all that. We've kind of taken a track that's pivoting away from embedded and more towards the data center, right? So our CEO, Victor Pang, has talked about data center first, which I enjoy because I think data center just means better software, better programmability, more support, and really focusing on key markets like machine learning, right, in the data center. And so 2018, we introduced Alveo, and these are great because these are cards that just like, discrete GPUs, you drop in PCI Express, it works, it's supported by Xilinx, there's not a lot of variability, and that'll continue on. So Xilinx has kind of pulled that board business in, and this is often when you go to the data center, you don't bring silicon, you bring boards. It might be blades, it might be racks, but in this case, we're bringing discrete cards. And the most exciting thing I think is, job security for the research field for a lifetime is the Versal platform coming in 2019. And this is kind of the first adaptive compute acceleration platform. I touch on key pieces. We'll actually be doing 2 papers at FPGA, the conference FPGA, that's in February. So If you want to hear more, I encourage you to come there. There'll be one on Versal itself and then one on the network on chip. And clearly for this community, the AI engines are being added. So we're adding hardened cores that are targeted for AI. But we're also, more from the FPGA side, which I think is interesting, is the network on chip. So we've hardened the network on chip. So architecturally, that means you can get around the chip much faster. It'll change how you design. We talk about the tooling and how sometimes it takes a long time to compile. You'll actually be compiling around the network on chip rather than trying to do a monolithic design. So that's kind of our story of where Xilinx is today is that we're trying to push into the data center, unify around platforms, unify around boards, and hopefully that allows Xilinx to focus its efforts on customers and you all. So that's where Xilinx is. Now, on the ML side of the house, we clearly focus on inference, right? We see inference as the place where there's going to be the largest growth. There's going to be a diverse set of applications, and they'll be, again, infused inside larger applications that will really benefit for what TVM is doing and what you all are working on. So there's lots of graphs that show the complexity of ML. I'll just show two from our end. And one is just looking at the frameworks, and you guys know this better than I do, right? The frameworks are changing, they're evolving, they're targeting different platforms, they're better for different things. TVM clearly comes in and is really helpful for us on the architecture side because it's very hard to target multiple frameworks within small teams. And the workloads are evolving, right? And it's not just the inference part. Again, it's how it integrates. Is it talking directly to the network? Is it coming over a cloud interface? Is it an edge device? All these things matter. And clearly, as you guys all know, we're moving to lower precision, which is great for architecture exploration because, int8 wasn't really an option, right? So many years back on some of the discrete parts. But we talk about going even lower, and I think you see sometimes the 1, 2, and 4 bit, right? But for us, it's about performance per watt with a similar accuracy. So we really push for the similar accuracy, and that leads to great training questions and great research. And clearly, Xilinx is bit-level devices, right? So it supports this natively. And I didn't hear too much talking about, but the idea of compressing the networks, reduce compute and memory needs. One thing I didn't hear too much about is we often see customers who want to encrypt the data, and I think we talked about a little bit about the security enclaves, but people don't trust. If you steal the weights, it's almost like you're stealing a lot of proprietary information. So there's the compressed networks, and there's a lot of work you have to do, which is I see again as part of the whole application. The other graph we kind of show is, and again this is Xilinx, it's interesting at an architecture side is to say, if you just look at the giga-ops and the megabytes of data required, it's all over the place, right? So as people compress for, look at mobile, some of the networks go there, but clearly some of the speech recognition, which are kind of at the end, are off the charts. So, one architecture to solve the problem, it might be good. We see, often we're good for some, but not good for all, right? And we highlight the L3 cache size, not to knock processors, but just say that, oftentimes it's really hard to keep all that on chip. And so then you get really novel memory subsystems and really interesting caching architectures that people really like to research these days. And 3 points, sometimes, inference is hard, right? The training is really hard, but the inference is actually hard too, to make all this work in small packages. And there's huge variations, and they just, they're not staying on chips. So that's, again, great for FPGA since we have options around all of that. Let's see if that. The other one, when Xilinx often talks about the total cost of ownership, and one of them is power. And oftentimes you spin up an AWS instance or your own machines, you don't really know the power, right? But a lot of people who run their own data centers they're concerned. Power, you have power budgets, right? And that decides what gets put in oftentimes. And this is a fun. We like this graph because if you look, it's power consumption, but you want lower for error rate, but you want lower power. You kind of want to be in the bottom the bottom left. And what's fun about this is just one example with LSTM is that you can see it's a 3-bit wait, 8-bit activation. So, you know, who's supporting 3-bit waits, right? That's, you know, who would think to do that, right? But that's something we see graphs like this all the time where people are exploring different weights and even seeing mixed precision, right? So different layers having different precisions, right? We do see that in the field. And there's nice graphs that you can kind of do some theoretical power on the ASIC side as well, just to give you some ideas of the power consumption. So those graphs are fun for us to look at. So now I'll talk a little bit about the two architectures. I think a gentleman asked a question about the two architectures that Xilinx has, and these are kind of the productized architectures. We have a ton of research architectures as well. So the one in the cloud that Xilinx has kind of pushed is called XDNN, and what's kind of fun about it is that there's a couple things where, you know, typically we do see lower latency because we're not worried about, you know, latency hiding and all that stuff and memory bottlenecks. We kind of keep everything with the core. So we typically, you know, see lower latency, sometimes an order of magnitude over CPUs and GPUs, just because we're kind of, that's how FPGAs are built in the architecture. But then the performance per watt is in low power is, you know, typically you'll see a 2-to-1 on the GPUs, right? And that's what we typically look at against. But I look at the 3 bullet points on the right, and the thing to remember is that these are built in programmable logic, right? So we evolve our processors as we learn from the community, as we engage with people, you know, like us all at TVM. But, you know, the one thing is we can build that, and the first thing people said is like, well, let's have throughput and latency variance. So we actually built different cores depending on what you care about, and it's the architecture, right? And then the tools can adapt to that as well. And I kind of joke about the CPU offload for new layers. We call it software deceleration. You know, so we talk about TVM has, you know, CPUs, GPUs, and accelerators. It could be FPGAs and decelerators, right? If I'm being cheeky, but, you know, with all due respect to all the good work that goes on. But we use software as an offload mechanism for when you want to explore a new layer and just see it working before you have to go through the effort of programming the FPGAs, right? And we know that can be a big step for a lot of people. But I highlight 3 things about it in general. Seeing the systolic array, if you saw Vita, you often see a similar, I know you maybe can't read the text, but you often see an array in the middle and then some operators below and then big crossbars and instructions, right? So that's typically what you see. This isn't unique to us. This is what you would see in a lot. If you looked at TPU, you know, block diagrams, even though they're ASICs, you'd see some similar style. And the other thing I'll notice is that these boards are available on the cloud, and everyone knows that here, I guess, because everyone was talking about AWS, and a lot of people don't know about Nimbix, which I'll talk about later. But they're available, and then we try and open source a lot of the tutorials and a lot of the labs around it, so you can at least reproduce the results that we claim. You know, and I think that's a nice thing for Xilinx to be doing. The other one, which I kind of more enjoy, as XDNN was built in-house, DeFi was, you know, came out of academia. It really did. It was one of those projects, you know, mostly driven out of Stanford, but, you know, Bill Daly was attached to a lot of these, and they had really groundbreaking papers on both pruning, compression, and some quantization work, right? And they were well-received papers, and Xilinx enjoyed working with them, and so much so we bought them. Just like a lot of people do. And what's great though is now it targets a lot of the boards on the edge, right? So we keep XDNN in the cloud. It goes, you know, but we're hoping that together we'll learn from each other, and the compilers will kind of merge together. But you know, we just, you know, you can see the date is July 11th on 2018. More or less the deal completed in October, and then, you know, it takes time for integration. And the other part, you know, I like to think about ML applications is, I think we talked about some of the fleet management, you know, the VTM does. There's a lot of good stuff in the cloud that goes on around that as well. And so we were at reInvent, I guess it was just a couple weeks back, right? And we were talking about how do you manage machine learning at the edge, right? Because what's fun about, you know, things like SageMaker or other platforms is that you're actually able to train in the cloud, and you can deploy to hundreds of boards at once, right? And so this is I think something for the VTM community to think about is as you're in these environments, how nice it is, your edge devices, you can start connecting them together. And I think all the cloud providers are doing a pretty good job of trying to think about IoT edge devices. And so that's a fun part of machine learning as well, is just integrating with the cloud. So, I'll now talk about just briefly about Xilinx and open source and how it relates. This is more my area and how it relates to TVM. So, we do a lot on, we're coming up to speed, I would say, on open source. We've been an EDA company, a lot of government contracts, a lot of fear about things getting out. But at least on the machine learning side and some of the software side, we've tried to push more things out. And I highlight 3 examples. So I think some of them are familiar with we have quantized neural networks. So these, we used to call it binary neural networks, but then we decided to go higher, right? So we started at 1 bit and went up. So a little different, but but it made sense at the time. And then we also, for some of these PCI Express attached FPGAs, which would be, Amazon's a little more protective of how the FPGA is used. But if you have those Alveo boards, the runtime is exposed, which gives you better options to manage the memory. I mean, that's king in a lot of applications, so we allow that. But I'll focus on Pink just for now, because that's the project I maintain and I run, so I get to talk about it. But the reason we see Pink, and we see Python as a productivity language that never really touched the edge, right? It was Raspberry Pi, it was kind of there, but we never saw it for hardcore industrial strength devices. But as you guys know, right, Python kind of ranks as a really high language, and that's fairly consistent. But the thing you might not know is that now it's kind of listed as an embedded language. So this has a lot of, you kind of raise your eyebrows if you're an embedded person, because C and C++ is king, right? But and I think that's still in the 95% of designs in embedded use C and C++. But Python is coming around as devices get more powerful, right? As you can imagine, that would happen. And you can see the growth trend in languages as well. That's something we're interested in. But it's really driven by ML, right? It's driven by ML, driven by academia. I think I've talked to some people here today when it's challenging to see a resume and you see Python, or you see I'm an ML expert or a data science expert. You really have to dive in, because it may not be a computer science background, or even Justin's talking about machine programming, right? They might be very high up there in the space. But what we do is we do a couple things where we take our embedded devices, which are Zinc and Zinc UltraScale, and we try and make them look almost like cloud devices. So we use Jupyter notebooks as our front end for embedded devices, and that's somewhat unique, right? I think you see a lot of people use Jupyter as a learning tool kind of for ML or vision, but we actually use it directly on our embedded devices. And Pink enables this on all boards. And what's nice about this is when you're thinking about your FPGA architecture and you're thinking about TVM as a compiler target, Pink is nice, because then it becomes a platform target as well. So as your design is pulling up into higher level languages, we actually now we ship pip installable designs, right? So that gives you, as you think of entering into ML frameworks, right, we're more interested in all the frameworks, which you often find, again, ML attached to other packages as well. And then we ship it as an SD card image, which is almost analogous to us, focusing on a single board in the data center. What we're trying to push here is we're giving you single software experiences, regardless if it's a $10 part or a $10,000 part. It doesn't matter to us. And what I like about this, and, I think as an academic community, it's getting people excited about what you're doing, getting excited people about computer architecture, getting them excited about how ML can affect the world. And we put this out there and have an interesting sweep of community projects. So if you want to see different neural networks, maybe VTM targets in the future, you can sweep across our pages. But what's fun is a lot of people then interact them. They put the ML, they might include it with a robot, they might include it with different displays, motor control. One One wonderful application of machine learning you might know is predictive maintenance. So instead of waiting for the device to fail, you predict when it's going to fail, and that's huge in industrial IoT. So ML has places on the edge that you might not think of, but then it can also integrate with, clearly vision is a big one, as you see vision pipelines often in front of ML inference engines to do some of the video parsing. And you know, we have good, dug this up out of my email. This is Thierry asking to join our forum, and he's, you know, just very nonchalantly just looking to use pink boards for a course at the University of Washington, and that's really been nice, right? I think we've had a good relationship on the forum, and we're hoping to pay it back with some engagement with people here at the University of Washington, with Louise and others. So that's been very nice for us, right? Because as you know, FPGAs have kind of, you know, stayed in the embedded space, but we're hoping to push it forward. And I'll highlight some other engagements. And I cherry-picked these to relate to hopefully some of your interests, because I was trying to look through the topics and understand what people were interested in that we could talk about. But you know, clearly the VTA, anywhere you see a pink board, you know, you can see where we are. But clearly we want to engage there. Dustin Richmond, who was at San Diego, is now here with Michael Taylor. So if you're interested in RISC-V architectures and how they can relate to machine learning, he's here. On the Xilinx research side, we have all sorts of BNNs and QNN network that you might be interested in. I mentioned FireSim because Chisel's awesome, and the guys at Berkeley are doing a great job, and we hope to engage with that as well. And then some other projects which are kind of fun. If you're familiar with MicroPython, it's a small variant. So if you want to do some neural network work on even smaller devices, MicroPython works just fine. And caffeine is always good. So I just mentioned there's lots of places for machine learning to get your work out in applications. So my last slide kind of here is just to say, you know, we have a couple ways we'd like to engage with you all. And one, people didn't know this, is that those Alveo cards, you can get free hours on Nimbix, right? So it's not AWS, but Nimbix has a really nice Alveo cards for you to try out. And look at our community pages, and we have two DAC 2019 design contests coming up. So please check that out. And finally, I hope I've just given you an overview of why I think Xilinx is great for exploring and deploying inference. And we hope to actually engage with you. You have my contact, and instead of me trying to hire you, just come visit me. And if you visit Boulder, Colorado, I think it's easier to hire you. So thank you so much.
All right, thank you. All right, do you have one quick question for Graham while we context switch? Yes.
Are you looking into deploying for inference other models such as decision trees?
Oh, I think for the other AI kernels, I think most of the emphasis hasn't been on machine learning, but there are community projects around decision trees and other AI kernels. So online learning is typically really nice for us because we want to be in the data path as well. And so that's an area where there's all the other AI kernels. If there's anything unsupervised or online, I think we have a nicer story because we can do the data path as well. So.
All right. Great. All right. Thank you again. Okay. All right. So now let me introduce you Professor Zach Tetlock, who's going to be our MC for the whirlwind of lightning talks. Why are you introduce yourself? I'm going to set up the computer.
All right. Good evening, folks. I know that it's been a long day of talks. They've all been pretty incredible so far. So we saved the most shocking results for last here in the lightning session. Wow.
You're starting well, Zach.
I'm telling you, the lightning speakers, you guys are in for a tough audience. But we do have a bunch of folks. We're going to try to keep things lively. So everyone's been told they've got a 3-minute time limit. So if you see the crook coming off the stage, that's what's going on. We're going to try to keep people on track. If Matthai from Microsoft could go ahead and, oh, okay. Great, it looks like we're just about set up. So first off, we're going to hear about efficient activity detection. So do you want to go ahead and start? And I'll have a timer up here just to keep people on track.
So I just wanted to give you a report out on some work we've done on ultra low precision inference on the edge, voice activity detection in this case, jointly with Josh Fromm, who's part of the UW TVM community and various others. So the voice activity detection problem is what you think it is. You have a voice signal coming, and there's human voice as part of it, and you'd like to detect very low power very quickly if it's human voice. Traditionally, before 2016 or so, you had Gaussian mixture models running. And the state of the art on reasonably challenging data sets was around 20% of error, but pretty good latency, 70 millisecond latency. And you get typically a fraction of a CPU to run on these things. So you need nice optimized code running sort of in an embedded way. Okay? So the obvious answer was to try to use a DNN here. This is stuff that we did about 2 years ago. At this point, the work kicked off with our colleagues. And they put together a fairly simple DNN that took a window of a spectrogram, the frequency spectrum, just a few fully connected layers. And they got awesome error, 5.6% error from 20%. Everyone's happy, of course, except that this kind of DNN is very slow. The latency of running it was very, very high. So there are many ways to optimize this kind of DNN. You can actually factorize the architecture and so on. The particular direction that we decided to try was to try to quantize it. We actually looked at various other options as well. This is ultra low power, low precision quantization, so 1 to 3 bits. So just to understand how 1 to 3 bit quantization works, just to be clear, you take the kind of floats that you have, convert each of them into +1, -1 essentially. And when you look at the kind of multiplication table of +1 and -1, it looks like an XNOR. So you can kind of pack your 64 numbers into one 64-bit digit, do XNORs, do population count, and get much faster implementations. And of course, the model is also very compact. In terms of number of operations, because your n numbers become n over 64, you have essentially about 40x fewer operations. Op count, of course, this doesn't actually necessarily mean speed up, and it's much more compact. So this has always been the promise of ultra low precision. The problem is if you try to run this code, it will actually be slower because you're competing against extremely highly optimized gem code out of MKL or something like that. So you need highly optimized implementations of this, and this is where something like TVM and so on comes in. This is my last slide again. The next try is with a custom gem operator where we produced a tile factorized, vectorized, fused version of this thing at different quantization levels. So this is starting from 32 by 32 weights and features all the way to 1 bit. The 1 bit version has about a 15% error, which is much lower than the 5% we're shooting for, but the 2 bit had about 8% error, and it was actually 30x faster, which means that we are at now the 5 millisecond latency. Okay, so it's kind of a very nice flow here, able to take a fairly simple model, crunch it through the compiler. In this case, we actually used Halide because this was before the TVM days. And this really shows how, what compilers can buy for you when you have new ops, especially. Thanks.
Okay, and we might have time for one quick question. Any short ones? Okay, start thinking for the next talk. Up next, we're going to have Josh, who's going to tell us about fully binarizable?
Yeah, not quite. That title is a little outdated.
Something like that.
There it is. Okay, hi, I'm Josh. I actually, the same guy who worked with Matthai on that previous one. I'm going to talk to you about a different type of binarization network that we did recently, and it was published in NeurIPS. And the slides are automatically advancing. So Matthai kind of gave you a, I have no control.
We're going to keep you on time.
Yeah, okay. Makes it a little tough. Yeah, so we talked about binarization. I don't think I can go that fast. Basically, the idea is that 1-bit binary accuracy is quite bad. It's only like 44%. And 2-bit binary accuracy is very high. It goes up to like 53%. That's a huge gap between the two. Yeah, I can just go back. OK, good. Let's do that. Right. So on the right here, we have the accuracy of AlexNet trained on ImageNet with different numbers of bits. So you can see at 1 bit, we have pretty bad accuracy relative to 2 bits. But the downside of higher bit width is that you lose all your benefits, right? You're now half as fast, and you use twice as much memory for your weights. So the motivation behind this paper was how do we kind of bridge the gap between 1 and 2 bits, which is this substantial chunk of performance that could be gained. So traditionally, you kind of binarize an entire tensor to either 1 bit or 2 bits or n bits. But we want to create a fractional bit width. And so the idea for that is, what if we just sprinkle in some higher bit width parameters into the tensor so that we have an overall fractional average? So for example, you could do a small number of 2-bit values to create an average of 1.4 bits. The question then is, how do we pick which values actually get the higher bit width? So for that, we have to kind of understand how higher bit width binarization is computed. And essentially, each bit is taking a step towards the kind of like the, to reduce the error of the true tensor. You're reducing the approximation error with additional steps. But if you, the values that are close to the mean for any individual step actually don't need extra bits. They're already a decent approximation. And because of that, if you sort by the difference between all the values in a tensor and the mean of those values, and assign the lowest bit widths to the, the values closest to the mean, you end up with a pretty good way of assigning the bits. So we try all these different ways of distributing the bits. If you just randomly throw in high bit widths, you get kind of low accuracy. If you assign low bit widths to the largest values, it doesn't work well. If you assign low bit widths to the smallest values, it doesn't work well. It works great when you assign them to the values near the mean. This actually gives a super linear scaling. So not only does it allow you to tune your performance to speed trade-off, but there's a representational advantage. And at 1.4 average bits, we actually do slightly better than 2 full bits of binarization. So we're doing more with less information, which is pretty powerful. This applies across both AlexNet and MobileNet, which we use to just test that this algorithm applies to state-of-the-art models. And we have like very good results relative to other binary implementations. One downside is that it's a little hard to implement. On CPU, we need sparse tensor library support. And in custom hardware, it actually lays out really nicely, but engineering FPGAs is difficult. Right? It would take a lot of man hours to do. And so this is where TVM really comes in. It can help us implement this efficiently and get the big accuracy benefits that we see at training. And that's all. Thank you.
Any quick questions for Josh? Okay. Meghan is up next. We're going to hear more about generating fast operators. And how do you pronounce this? It's binarizable? Binarizable? I struggle with English. Okay.
Josh has previously shown you can train binarizable networks, but it's actually hard to generate fast operators for these networks. So the big problem here is most of these networks are trained in frameworks that have no binarizable operators. So you can't measure the performance gains, and it's also very easy to introduce bugs into these networks. So we need a way to generate these binarizable operators ourselves. So one of the challenges we have is the baselines are incredibly well optimized. So 32-bit floating point, 8-bit networks are actually very fast. And without optimizations, low precision operators can actually be slower. So we want actually operators that are faster than the baselines. But we also want them to be able to target different types of convolutions or operators, as well as have performance portability across different CPUs. So here we generate fast operators using TVM. So here's a small section of the stack that's relevant to our work. So using the tensor expression IR, we can declare the bit serial computation as well as a schedule, CPU schedule describing the optimization space. And then we can leverage AutoTVM to find scheduling parameters for different backends so that they're optimized for different CPUs as well as operators. And then finally, we can overrule LLVM's code generation with custom microkernels. So here we use TVM's tensorize primitive to replace like the innermost loop of computation so that our operators are highly optimized. So on a Raspberry Pi, we were able to generate operators for 1-bit, 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 2-bit, and 2-bit, 2-bit. So here we show across the different convolutions of ResNet, we can gain between 5.5x for 2-bit, 2-bit up to 15.2x faster than an optimized 16-bit baseline. And okay, yeah, that's it.
Any quick questions for Meghan? see a hand. Okay. Okay. Can we actually have Morita next? Does that look good? Okie dokie. Here we go.
Okay, I'll explain OpenCL backend for FPGA. I think Vida is great, but this is yet another approach to support FPGA in TVM. And so, why HLS? Debugging software is much faster than hardware. For example, we can make use of software to like GDB or Valgrind for development, and it's easier to specify functions in software. And why OpenCL? TVM has already supported OpenCL for GPU, and we can share code base with it. And we can also support Intel and Xilinx FPGA with the same code base. And I'll show one example of OpenCL backend for Intel FPGA board. We use AutoScheduler backend for it. And it is already supported in TVM. And we can also make use of software emulation for it. And this example targets for D10 nano SOC devices for edge environment. And the target graph is a compute layer of the tiny YOLO V2 models. Recently, I demonstrated with TVM object detection with tiny YOLO, and this talk is based on the experience. And with D10 nano, it takes 3.8 seconds with ARM CPU of D10 nano, and let's offload this layer into FPGA with AOCA backend. And this is the generated code with TVM, and unfortunately, the performance result is 7.9 seconds. It's much worse than CPU. And all the loops are pipelined, and II is 1, but why so slow? It is because the bottleneck is reading global memory. Reading global memory is redundant, and we should optimize it. And in this talk, I focus on this optimization. We can reorder the loops and caching the global memory A, and we can reduce the number of global memory reads. And with this optimization, the number of global memory reads decreased from 1,500 to about 200. And we can do this transformation with the current version of TVM, but we can do more optimization. And the problem is the size of cache is big. If we unload the outer loops, the cache size is bigger. We can use shift register, and the size of cache is constant, and we can read multiple data with one cycle. And finally, I got 0.2 seconds with OpenCL. There are many other optimizations, and please ask me later if you are interested in. So what are required for TVM? We should support more pipeline-friendly operations, I think. For example, how we should implement historic array in TVM. And we also support schedule operation for FIFO. I think we need something like pipe read and pipe write. And it looks necessary to support channels or shift registers. We also need heterogeneous executions, and I think it will be supported in relay in near future. For further improvement, area optimization is important. This is the result of offloading whole ResNet networks. And there are many redundant codes in kernels, and we should remove these duplications. And performance optimization is also important. This screen capture is the result of OpenCL profiler, and it consumes many times in data transfer between host and devices. And you should make use of channels to data transfer between kernels. And I think there are many parameters for OpenCL backend, like the number of unroll loops. I think we can use µTVM for it. Thank you.
Thank you very much. It looks like there's a lot of exciting opportunities for compiler optimizations in this space. Part of what's so enthralling about Relay. Up next, we have the other Luis, right? We have Luis too. We're going to hear about how we can make our own Vita design. So.
Okay. So I'm going to be talking today about how to build your own Vita design with Chisel. My name is Luis Vega, and basically I want to first talk about our vision. So I'm going to be covering like where we are today and where we're heading. So currently today we have support for Vita only on edge Xilinx FPGAs, but we are thinking on pushing this forward, and we are going to support Xilinx edge cloud FPGAs as well, and other cloud FPGA vendors, and as well on ASICs. Currently, what we have as a Vita design, we call this off-the-menu selection design, but we are heading towards build your own customized Vita. So we're gonna add more parameters, so we can have better, more configurations, basically. Also, we're currently focusing on inference, as you have already seen on different talks, but we are focusing our efforts in training for the future. And currently, we support only dense workloads, but we are looking forward to incorporate sparse workloads as well. So the way we see the Vita in the future is actually about having a generator. So a generator that allows you to create Vita designs the same way you customize your, basically, you can do the analogy with a Domino's pizza order, right? Like you can imagine having a Vita design that has a Xilinx cross or a Intel cross or a 28 nanometer cross. And also you can have different sizes, like whether you're going to deploy this in the edge or the cloud. And you can customize this design with different data types, for example, or enabling compression. Also, we are exploring having like different architectures from SIMD to systolic array. So the idea is like to have a way of expressing all of these designs. So one way of doing this, we believe, is Chisel. Chisel enables these hardware generators. So Chisel is this hardware construction language developed at Berkeley, which is based on Scala and allows you to have efficient code, extensible, easy to parameterize, and covers a lot of targets. And it's also very maintainable. So Chisel has a lot of success stories. So Berkeley alone has just taped out 17 chips in the last 7 years. And it also like proved to port different designs for different of these vendors' FPGAs. And as a timeline, this is a project that we started out September this year, and we are planning to finish it up our RTL simulation for this core at the end of this year, and we are going to have an FPGA prototype in the first quarter next year. Thanks.
Thanks, Luis. Any questions about build your own Vita prototypes? Okay, Pratyush, come on up. Up next, Pratyush is going to tell us about µTVM, which is appropriate for a short lightning talk, right? So, good luck.
Okay. Hi, everyone. I'm going to talk about µTVM, which is about bringing deep learning and machine learning to bare metal devices. Let me start out by giving a motivating example. When I was interning at Microsoft Research a few months ago, they were building the smart cane. And the way this worked was they had a microcontroller, which was an Arduino, running an inference model, and which detected gestures. And these gestures were converted into actionable output on mobile phones. And it's not just an assistive technology that we have seen a proliferation of such tiny devices, but rather in a variety of domains like IoT, sensing, agriculture, and so on. And there's something common among all these tiny devices, which is that they don't have a full-fledged OS stack. And the goal of this work is really to support TVM on these bare metal devices so that it has a much broader impact. It's not an immediately straightforward way to do this because LLVM and CUDA, which are the primary backends of TVM, are not really supported on these devices. And as a result, we have ported TVM to also support C and C++ backends, which has been upstreamed to the GitHub repository. So you can go and try it out now. What this enables is that we can now support backends like RISC-V, Arduino, and many other backends which only have GCC support. The way we envision µTVM to work is essentially very similar to AutoTVM in that you send a program to the board, it produces some output, you send back feedback to the runtime, and it can optimize over this process. But there are certain differences in the way the interfacing is done with the board because of the resource constraints. First is that you don't really have a RPC layer, so the way we interface with the board is by using a hardware debugging interface. And this essentially lets you read and write to specific memory addresses on the board. The TVM runtime generates C code, which is compiled into an object file using a vendor-specific GCC. For instance, in RISC-V, this could be a RISC-V GCC. And the TVM runtime then reads this binary and translates the addresses into addresses that actually correspond to the board. It also introduces certain new memory sections that are required in order to drive execution on the board. Once it has the remapped binary, it uploads it via the OpenOCD interface, and the execution can take place. Although this is still a work in progress, we have certain directions that we want to explore. The first one that I think is super interesting is configurable model sizes, by which I mean you specify an upper bound on the model size that you want on the board given to its memory constraints, and then optimize over that maximum model size. Another direction that we've also been considering is the quantized data representation and fixed point formats, which will give improvements in terms of energy efficiency and performance. Thank you.
Okay, yeah. Up next, we have Jenq-Kuen, who's going to tell us about supporting TVM on RISC-V architectures.
So this work joined with several group, include people from Patel group, also people from Andis. Andis is in the RISC-V foundation and supporting the RISC-V IP. So currently, in addition to the basic RISC-V architectures, there are actually two better ISA architecture extension to support possible fallback engine with AI models. And one is the traditional superworld vector proposed by the Esperanto, and the other is the subworld Cindy vector proposed by the Andis. And both of them are actually almost in the RISC-V specifications. And this work, we have also had team work on the superworld vector, but this work is more on the subworld Cindy. In that, they only support the fixed point instruction and integers. For supporting the TVM on that, we also have to do the quantization and also support the subworld Cindy computations. So to support the TVM on RISC-V with subworld Cindy computation, we add a RISC-V target in TVM co-design phase. The TVM RISC-V co-design co-generation will lower the Cindy computation with subworld Cindy intrinsic. And the LVM backend, we need to generate the corresponding Cindy instructions. So there are basically two ways to make things work. One is to have the TVM vector into the LVM vectors. So that's normally done for the like superworld vector. But the subworld SIMD is really sort of a pseudo vector. It's not really a red vector that take a subworld and pack here and there. So LVM compiler normally is not good in generating the subworld SIMD. So we elect to have the TVM vector lowering into the LVM subworld SIMD intrinsic, and only have the LVM compiler to generate the intrinsic into the RISC-V subworld SIMD instructions. In addition, there are ongoing work. We also try to do the quantization because the subworld SIMD only support the integer and phase point. And to make more software can be worked in that part, we have to all do the quantization. And currently we use a format in our spec to be more with the OpenCL Next. There's a proposal we sent to the OpenCL Next for the phase point feature set. In that we can specify the width and also the binary position in the phase point. So this is an example in the matrix multiplication. So if we have an honest model and with 16-bit, and we can load into the LVM and with the SIMD instruction set. And if with the LVM, we load into further with the SIMD assemblies. In that, when we run the program, we use the spike simulator to providing the execution. Out of 229 instructions, currently we generate 104 subworld SIMD instructions to actually run in parallel. And there are also some packed and unpacked instructions that can be also further tuned and optimized. So a quick summary that we also talked to AWS team to try to hope to add the RISC-V backend for the deep learning compiler, also hope to contribute the code to TVM source trees. And currently, our work is more based on a spike simulator, and they don't have a lot of detail with architectures. We hope to try to get the real chip and also work with the more detailed simulator like Jenq-Kuen and C simulator, the more memory model, and then we can tune the performance. Thank you.
Thank you very much. So up next, we're going to hear from Gus on building your own data types. Okay, Gus, take it away.
Hi, everybody. So I'm going to talk about bringing your own data types into TVM, which we've talked a lot about today. I don't really think I need to, at this point, motivate why we want to bring data types into TVM. We saw Meghan and Josh talking about truncating and even quantizing down to integers. We've even talked about posits today. And even Andrew was talking about Facebook's explorations into deep learning hardware that's using these new different custom data types. So it's clear that people want to use custom data types. What we want is to make that as easy as possible to do in TVM. So that's what this talk is going to be about. So our goal in this project is basically to allow developers to bring their own data types into TVM. And we mean that very literally. What we mean is you're already using your custom data type library. Let's say you're using something like softposit, or you're trying to use posits. So if you wanted to use posits in TVM, all you should have to do is call out to softposit, or whatever library you're using, at the correct points in TVM, and TVM should do the rest of the work for you. You shouldn't have to re-implement your data types inside TVM. And the good news about this approach is that right out of the box, it's going to work with AutoTVM, because all AutoTVM has to do is tune over the schedule of calls out to the whatever library you're using to implement your custom data type. And so far I've just talked about the current goal, which is software support for custom data types. Really, in the future, what we're interested in is bringing support to TVM for hardware custom data types. So one example that we're going to pursue in the future is bringing in open source hardware implementations of custom data types into Vita. So something like Facebook's DeepFloat, for example. And even further down the road, we could think about tuning over the actual software and hardware implementations of these data types to create new auto-tuned data types. And so now that you understand what the goal and what the visions of this project are, let's look at what you can actually do with the code that I have on GitHub today, because I think that's really what's going to motivate people to go and use this. So let's say I want to go today and add a custom data type and use a custom data type into TVM. Well, what can I do? So this is an example of some Python code. The first thing I'm doing is I'm registering a new data type called myFloat here. And then I'm writing this simple TVM program here, where I have this input x, which is an input of tensors, and I am essentially just casting it to a tensor of myFloat. And so myFloat is the custom data type in this case. Not exactly the most interesting problem in the world, but it's a good example. And so then in TVM, I basically just build, and I give the input and output, and I run the program. So to make this Python code actually work, to enable TVM to actually build and run this code, what do we need to do? Well, what we need to do in TVM is we need to tell TVM how to lower every instance of our custom data type. So in this case, this is actually all of the C++ code needed in TVM to make this example work. And exactly what this is we're telling TVM how to lower a cast of float to myFloat. That's all we have to do in this case. And so most of this code, most of the C++ code here you can ignore. It's just really this last line that's interesting, and it kind of shows you how this cast is implemented. Essentially, this data type isn't all that interesting. We're just taking the input float and we're reinterpreting those bits as an unsigned integer. So myFloat isn't exactly the most interesting data type, but it doesn't really matter. This is a simple example. And as you might expect, this code runs, and the output is essentially just the input float bits interpreted as an unsigned integer. So this program, like I said, doesn't exactly do anything useful, but really what this example is meant to show is that you can go out today and pull this code from my GitHub and use it. So go ahead and start experimenting with your own data types. So like I said, I'm hoping this got some people excited to go ahead and start experimenting with their own data types in TVM. Here's my fork on GitHub. Go ahead and start experimenting. I'm hoping to start adding something like posits in soon, but you might beat me to it if you're really excited about this. And also, don't hesitate to reach out to me directly. This project is incredibly young. We just started it this quarter. So if you have any ideas, any guidance, it's honestly much appreciated on my part. So don't hesitate to reach out. Thank you, everybody.
Thanks, Gus. One thing I've been excited about, there's been a whole theme today on custom numerics. It's pretty radical to think about people ditching IEEE 754. I think there's going to be a bunch of good stuff that comes out from that. Lian Min, take it away. Oh, and we're going to hear about an AutoScheduler for TVM.
Hello, everyone. My name is Lian Min Zheng, and currently I'm a research intern at the TVM group. I'm going to talk about the AutoScheduler for TVM. So currently, although we call TVM an automated compiler, there is still a step towards full automation. If we look at current workflow for adding a new operator in TVM, first we'll write the computer declaration in the tensor expression language, and then specify an AutoTVM search space. These two components will be fed into an optimizer, and we can get a final optimized code. This looks cool, but we still need some human effort to deduce the search space and write the corresponding schedule code. So when we talk about the tensor compiler, what people really think and want is just this blue line write down the computer declaration and get a final optimized code. They don't want to care about the search space tuning knobs. So we should definitely add this blue line into our stack. Here we introduce the AutoScheduler. Basically, it does two things. First, it will deduce the tuning space from the tensor expression, and then it will generate the schedule template for configurations in data space. So the general problem here can be very challenging, but as we have explored the space quite a lot, I think we can start to summarize the lessons we learned and automate this part for existing code base. So here I can take convolution to see how it works. So it starts from the vanilla tensor expression, and then it will analyze the axis relation between the buffer and the axis. I think this step is the most critical part to get a decent performance based on current existing AutoTVM. And then we will generate typical tunable knobs, such as multiple level tiling and computer location or loop annotation. Okay, so then we will map the whole configuration space into different backends. The usage should be very simple. We just replace all TVM $quiz schedule to AutoTVM $quiz schedule. And we can replace the 87 lines code for defining space and write schedule to only 7 lines code. This demo works, but the whole project is still work in progress. Our goal is to replace all manual schedules in current TOPI without performance regression, and provide schedules for new coming operators, such as training operators and more variants. So hopefully we can see the OpenPR in 1 month. That's all. Thank you.
Thanks a lot. Any questions? Oh, yeah.
Like in the highlight world, like AutoScheduler refers to something different, right? Like generating, like this still requires like a large AutoTVM search. So have you given much work to
So you are talking about the difference between our AutoScheduler and the AutoScheduler in Halide. Yeah, so like in Halide, they are targeting the code without shape, and they can like use constant tiling factor like 4.8, and they have a simple cost model like 10 times arithmetic cost plus something like memory cost. But like in TVM, we find our empirical search on the real hardware works very well, so we have to we will build this AutoScheduler upon the existing AutoTVM. So this is our approach. Okay.
All right, thanks. Up next, we have Jenq-Kuen from UCLA going to tell us about hybrid script.
Thank you for introduction. I'm Jenq-Kuen from UCLA. And today I will talk about my contribution to TVM, which is a hybrid script. So the motivation of this project is pretty simple. So TVM is specialized for those bunch of dense kernels in machine learning. And this kind of algorithm are pretty simple, just a formula wrapped by several levels of loops. And you have a DSL to write it. It's pretty simple. But the things that once you come to some irregular kernel like sparsity, or something like you need some cleanup for the kernels, you cannot easily describe it in TVM. And the current solution is not sufficient, for users to write this bunch of kernels, because it uses some module called IR Builder. And the things that IR Builder originally was not user-oriented. It's it's built for developers to write and to generate some IR node efficiently, so that they can do some golden reference of the IR body to write a test case efficiently. And also, this this module requires the user to know a lot of low-level details to write IRs. There are a lot of pitfalls that user cannot escape. And finally, the things that after you create a body, it's something static. If you want to run it, you need to cast it to an external operation node, and then you have a module and you run it. Once it crashes, I mean, you have no way to debug it, because it's already lowered to a AirVM module, a JIT. It's not a Python native. It's not a Python native function. It's very hard to debug it. And the solution to this is pretty simple. If you have if we restrict a subset of Python that can be lowered to that can be lowered to highlight IR easily, and then you can just do sanity check in this function. Once, once you have a data structure in NumPy, you call it and you get the result, and you may check it in Python to get some sanity, and then you can pass some, TVM placeholder, TVM tensors to it, and it will return a TVM tensor as the output, and the operation node and the IR body is already formed implicitly. Here is a simple example of how to use it, and after you got the you get the tensor and you get the operation node, it can be connected to those bunch of other compute node easily. Okay, I think that's it.
Thank you very much. So is this mostly intended like for inference or for prototyping, or can you also train with this, or like what's the?
I think it's only for prototyping, and I mean some schedule, some programmability which is not supported in.
So it's just
TVM.
flexibility for exploring potential operators.
You can just write it in it first to do some to play with it first, and then later maybe TVM can officially support it. And also I'm planning to to make it another backend. We can just dump highlight IR to this script subset, so that users can just play with the generated code.
Nice. Yeah. Thank you again. So up next, quantization for TVM. Zhiheng. Okay.
Hi everyone, I'm Ziheng Jiang from University of Washington. I'll introduce you to quantization for TVM today. So what is quantization? In a word, it is to convert weight value to low bit integer like 8-bit precision from float point without significant accuracy drop. So we have talked about it a lot in previous talks. So here is a pipeline for common 8-bit quantization procedure. So assuming we have existed neural network model and we train it in front-end deep learning frameworks like MXNet, TensorFlow, and then first we convert it to relay our high-level graph IR. Then we apply the quantization algorithm and to gain the compression and the acceleration. After that, we deploy it on resource-limited edge devices like mobile, Raspberry Pi, or like FPGAs. So here are several advantages for quantized model. It uses less storage space, and the arithmetic operations are usually faster, and it is also friendly to accelerator and ultra-low power embedded devices. So when we try to implement quantization, we found that there exists a lot of choice space for it. So for example, the number of bits, we can use 4 bits, 8 bits, 16 bits, and we can choose different quantization scheme, so like symmetric or asymmetric. Also, there exist many hardware constraints. For example, some accelerators may prefer integer shifting instead of float multiplication. So our goal, instead of proposing the only right way to achieve quantization in TVM, we would like to build a quantization workflow which can be customized flexibly. So let's go deep into the details. The quantization procedure is composed of 3 passes in relay: is annotate, calibrate, and realize. So take a common RISC-V block, for example, is a conv2d, batch norm, ReLU, and another conv2d. So after annotate, we will rewrite this graph and insert simulate quantize according to the rewrite function registered by every op. And the simulated quantize op, it will simulate the rounding error and the saturating error during the quantization. And its argument will get trained during the calibrate to get the optimal accuracy. So after annotating and calibrating, we will realize this graph to a real low-bit graph, and then deploy it. And the simulated quantize op will get transformed into some small ops like multiplication and addition. benefiting from the graph optimization of relay, those all can be fused together to achieve the best efficient inference. So here is an example to show how user can customize their conversation strategies. First, user can override the annotated function. For example, it can choose signed int or unsigned int. It also can choose different rounding strategies like round, floor, cell, or something like stochastic round. Assuming we have an existing MS model, we convert it to relay graph first. Then we quantize the relay graph with all kinds of configure, like number of bits and global scales, etc. And with one more line of code, we are done with this conversation. And then we can build this quantized model and deploy it locally or remotely. So we demonstrate this workflow with 8-bit symmetric quantization to try different quantized configure. We achieve that 1.2 accuracy job on ResNet 18, and we also get great performance on like ARM CPU and our customized FPGA. So this feature is still developing, and welcome for contribution. That's all from me. Thank you.
Thanks, Zhiheng. That was great. Yeah, we were really excited about the quantization, and writing these higher level passes in Relay has been a lot of fun. Up next, we have Dominic, who's going to talk about another kind of vision involving machine learning, not computer vision.
All right.
Take it away, Dominic.
Yeah, thanks so much for having me. I'm actually not going to use the word TVM again. I'm going to talk about visualization. I build visualization tools and languages. And these languages and tools can help you understand your models or debug your machine learning systems. What's different about the systems or the languages that I'm building compared to visualization languages that you might have used before is that we're trying to map visualization concepts that you have in your head very close to the implementation of how you're actually writing it. So the goal is to have a language where the way you think about your visualization maps to what you type into the keyboard and then also to how you see it on the screen. The way we achieve that is through declarative building blocks, where you specify the what you want rather than the how you want to achieve it. To make this more concrete, here's an example. In an imperative approach, you would say, put a red circle here and a blue circle there. And that would be a way to specify your visualization. We take this declarative approach where we say you want to map a variable to the position and another variable to the color. And that's how you express your visualization. So what this allows you is that you can think about the data and its relationships rather than the implementation details. So let's make that concrete. Here's an example of a chart, this chart on the right, the scatter plot, in Vega-Lite. As you might think, there's some data that we're loading. Then we're visualizing the data with a mark point. And lastly, mapping the different variables to the x, y, or the color of the marks. And using these simple concepts here, you can create a wide variety of charts. These are all charts created with a simple language. We go beyond just the statistical graphics like scatter plots, bar charts, and so on, and allow you to also compose multi-view graphics with a similar language. And then we even went a step further and extended it and used similar building blocks to extend this language to support interactive charts. So you can specify, for instance, this chart at the bottom in about 35 lines of code. So far, this was in JSON. You might not be too excited about writing JSON, so we also support Python through a language called Altair. The way to use it is you import it, load a data set, could be any pandas data set, and then similarly to what you've done in JSON, write it in Python. And this is how you create this chart. You can add just a row to create a faceted chart, or add .interactive to have a chart that you can zoom. This and more is all on our website, and I'm happy to talk more about it. Thanks.
Thanks a lot, Dominic. Actually, we use Vega-Lite in all of our graphs for relay evaluation. So thanks for that work. Any questions for Dominic? Okay. Up next we have Christoph, who's from Qualcomm, and to tell us about Hexagon. All right. Yeah, take it away.
All right, so my name is Krzysztof Parzyszek, and I work at the Qualcomm Innovation Center in Austin, Texas. And I'll tell you about bringing TVM and Hexagon together. So I'll start with a brief introduction to what Hexagon is. Hexagon has actually appeared on one of the prior slides, but for those of you who are not familiar with it, it's, well, let me start with Hexagon, with the Qualcomm Snapdragon. So Snapdragon is a system on a chip, which means that it's really a bunch of smaller chips grouped together into a bigger one, and Hexagon is one of the smaller ones. It's not the main CPU, but it's one of the smaller ones attached to the CPU. The Hexagon on its own is really a full-fledged CPU itself. It can run any workload, but it was designed for computational workloads that can be done with a low power consumption, because the target application for it is our cell phones or embedded devices. And with the Hexagon vector extensions, HVX, it can process a lot of data with fairly low power consumption. HVX is really a vector engine that provides vectors that are 128 bytes long, which is 1024 bits long. So that's quite a lot of data that we can process. And so if you have a cell phone, there is a good chance that there is a Hexagon somewhere in it doing something. And so we have this capable architecture, and what do we want with it? Well, obviously we want to make it easy for people to use it. We want for what everybody else was talking about, which is to make programmers be able to solve their problems in taking advantage of all the features of Hexagon without necessarily knowing all of the architectural details. And we hope that TVM would be one of the platforms or one of the tools that we could deliver to make machine learning easier to deploy on Hexagon. So myself and the team that I work in are compiler developers. We work actively on LLVM. We have an LLVM backend in the upstream repository. And the fact that TVM uses LLVM as one of the backends was one of the factors that caught our attention and caught our interest in TVM. And we decided to implement support for Hexagon in TVM. And it's really a very fresh, very new effort. It's not, I cannot really show you exciting graphs with lines going up showing all the improving performance. But I can tell you that with what we've got so far, we were able to identify a cat in one of the test cases, in a picture, in a JPEG picture in one of the test cases that was supplied with TVM, which I believe is the equivalent of a Hello World for machine learning. So the way that we've done it, what we have so far is that we implemented Hexagon as the same way as a GPU. So taking a test case from TVM, what we did is that we simply changed, or the way that we envisioned, or with our changes, what we did to the test case is basically replaced CPU with Hexagon, and we set target equals Hexagon instead of host or LLVM, and we got it to work. So we got something working, but it's not really working as well as it could. And some of the major challenges that we ran into very quickly was that, first of all, we need data to be quantized. HVX and Hexagon generally operates on integers, and the test cases that we were working with were floating points. So that's not going to perform very well on Hexagon. And the second thing is that the model that we used, the treating Hexagon in the same way as a GPU, we need to be able to offload more than we offload right now. And we are looking forward to become contributors to TVM. And with all this work ahead of us, guess what? We are also hiring. So come talk to us, and thank you for your attention.
Thank you so much. sorry, we're running a little short on time here at the end of the day, but folks should definitely find Christoph super excited about these additional hardware backends for TVM. Okay, wrapping up the lightning session, Ahmed's going to tell us about AmorphOS, putting the OS in FPGAs. Good luck.
Hey everyone, my name's Ahmed Khawaja. I'm a PhD candidate at UT Austin. My advisor is Chris Rosbach, and I'll be describing our work on AmorphOS, which was published in OSDI this year. It's a much longer talk for that one and a lot more information, so I encourage you to go read that paper and look up the talk. So basically with AmorphOS, you probably guessed from the name, we're trying to provide operating system support for FPGAs. And why this is relevant to a lot of you is a lot of people here are focused on accelerators, and a lot of you seem to be turning towards FPGAs as a way of actually implementing those accelerators. So when we started this work, our primary goal was actually protected sharing. We saw these massive FPGAs in the cloud and multiple accelerators, and we were like, you know, it'd be cool if you could run 10, 20, 30 of these. In our work, we actually got up to 32 different accelerators to run concurrently on a AWS F1 FPGA instance. But a great strength of our work is when we define these interfaces, we introduce a natural compatibility layer. And this grants a great deal of portability. So for a lot of you, if you're designing your accelerator, you don't want to have to pick a specific FPGA, right? You might, if you write to this interface, it gives you a great deal of portability. So what we were actually able to do is we ran 15 benchmarks. We originally developed it on Microsoft's Catapult system, and then we were very easily able to port this to F1 without actually ever modifying the applications themselves. And then here you can see like an example of like an idealized case where you have multiple applications running concurrently. And a big thing we wanted was elastic scalability. So if you needed the entire FPGA, you should be able to have it. If you needed half, you should have it. If your application was too big, we should be able to shrink it down for you or shrink it up and then so forth. And then a lot of the work was actually how do you actually map this to the FPGA, how do you divide up the fabric and so forth. But for a lot of you, the more interesting part is the compatibility layer. So we see here some abstractions that we introduced, but long story short, because we're running out of time, if you look at the diagram on the left, you see that you have some hardware interfaces. So in this case, the Catapult shell, and then we have a set of interfaces that we defined, which is control, memory, and like bulk data transfer, which is what a lot of people care about. So if you look at like the VTA, for example, its boundaries are memory read, memory write. So whoever is implementing one shouldn't have to care, is your memory using Axie, is it using Avalon? It should be at that higher level of semantics, or DMA, right? No one here wants to implement DMA every time they switch FPGA boards. And then we have a very scalable interface. As I said, we were able to scale to 32 applications with very minimal fabric usage. Anyways, so I encourage you to actually go read the paper and then actually the longer talk that we've done. We do plan on open sourcing this soon. I'm currently nailing down the final iteration of the interfaces, because you don't want to release something and people start writing to it and you claim it's portable and then you're like, oh, I need to change my interface for whatever reason. So currently we support the Catapult system, Amazon's F1 and their cloud, and we recently started adding support for Intel's new Stratix 10 boards that just came out. And these are some of the workloads, including DNN Weaver, that I think some of you are familiar with, and also we're working on getting the VTA implementation running on top of our system as well. Thank you.
All right. So I think that I was really struck by all the shocking results in the lightning session. I think these folks deserve a thunderous round of applause.